Should I do it? That's okay, I don't mind. It's sort of like one of those cafes where you're doing poetry and, you know, the audience.
You just get started.
Anyhow, it's a pleasure to be here, and thanks to Dave for the invitation. So what I want to do in listening to this morning's lectures and thinking about ways we might have of interacting, I'm going to give you a couple of examples from, and I think this next session is going to be federal research centers or people who have thematic interest in what they've done in outreach. So at Rice University, I'm a professor of chemistry, and for actually a decade, I can say, I've been director of one of the National Science Foundation centers in nanotechnology. We were one of the first 6 centers that started in 2001. It was has been a Rice-only center, and NSF has the wisdom to sunset these research centers, so it will be sunsetting this year, which I think is a really good thing, actually. I think science needs to move on, and I'm glad there'll be another center coming along, and who knows what. But in any case, we have a lot of legacies that have come out of it, particularly in the area of outreach. So I'll talk about our particular view of that. And what you see on this sort of first slide is kind of an image of what the center is about. This is a nanoparticle. Nanoparticles are small, which is not such a big deal, under 10 nanometers by my definitions, but under 100 by the world's. They're often very perfect and crystalline, so the materials are organized, and they often have unique and strange properties. Strange if you don't know it or understand it, but actually one of the beauties is to understand their properties. So what you see here is an image of a nanoparticle kind of drafted off of C60 sitting in a pool of water, and that's really the theme of this center, which is to look at nanomaterials in environmental and biological systems. And the motivation, I'm not going to talk a lot about the research, although it bears on the outreach, is really the concept that by making materials really small, so this is a whole bunch of iron oxide nanoparticles, they're at the size at which they're really good single domain magnets. So you can remove them from water magnetically and use that process for water treatment in rural settings. You can use nanoparticles that absorb near IR light because they're like, this is a gold nanoshell. I like to think of it kind of like a peanut M&M, where the chocolate is actually gold and the nut is silica. In any case, these materials have been tuned to have very strong near-infrared resonances, and as a result, they can go into the body, and a near-IR laser can non-invasively heat them up to depths of 2 to 3 inches, depending on the part of the body. This material is actually one of the biggest outcomes of the center because it's in human trials now, phase 2 clinical trials for head and neck cancer. So it's a way of treating cancer cells that cannot be surgically removed or treated through chemotherapy. Another example is to use nanomaterials in high reactivity. You can design at their surfaces to clean water. And we have a pilot system now at a DuPont plant for TCE based on what you would think of as non-reactive metals, gold and palladium, but actually when they're nano, they become very reactive. So those are all examples of using the nanoscale world and what we can do with materials in these dimensions to solve real-world problems, which is the basis for many of the National Science Foundation's research centers. So our mission is to create sustainable nanotechnologies that improve the human health and the environment, and that's what we've been working on the last decade. However, there's a lot of other work beyond our research because to realize this mission required that we have pretty active and in some cases innovative outreach programs, ones that had not really existed before in federal research centers. And I'll tell you about those. Some of them are going to look familiar, especially our teacher training. It might have some twists that you haven't seen, but I'll talk then also about this word sustainable. If you're trying to use nanotechnologies to clean up the environment, you better not be creating a new problem. And so what sustainable means and what the risks of nanotechnology might be to people in the environment have been a really important part of our center. And that has actually defined a lot of how we've talked to the public about what we do. Some of our research highlights, we mentioned sort of the nanoshells. We do a lot of fundamental science, a lot of carbon nanotube work, so the full gamut of activities. But I'll just highlight this picture of the worm. This worm is black because it ate carbon nanoparticles, which happen to be black. And so we've done a lot of work on ecotoxicology, understanding biodistribution and fate of engineered and natural nanomaterials in the environment. Okay, so beyond academic research, most of the federal centers in the country from NSF, which in fact I've been at many meetings talking about outreach, it's remarkable how broad and how well funded these programs are. So in our roughly $32 million center, about 15% of that budget went directly to educational outreach. A little bit on the high side, but NSF has recognized that kind of putting that activity in centers has been important, and I've really been fortunate to have a number of great people to work with, which I'll talk about in these different programs. And so our outreach has really covered everything from teacher training to informal science at museums. but I think the part that I'm going to sort of emphasize is what do you do if you're trying to talk about science, but you're doing it with respect to risk? What science, the controversial questions that need science to sort of illuminate people's understandings. So a little bit of our outreach activity. I want to quickly say that we've really emphasized teacher training for over a decade, and that's really because of one of our first educational outreach directors had a really good experience in HISD. We have the 9th largest school district in the country. It's also one of the worst school districts in the country with respect to dropout rates and any other statistics you might imagine. In any case, she had a program that was inquiry-based middle school science education, and it developed laboratory experiments both for teachers and students, which translated into the school district. And from that start, we sort of built on her successes in the first few years of the center and grew a really strong teacher training program, which impacts a lot of different school districts now. We've done informal science ed through a lot of our nanotech centers. Nanotech is actually very visual. You've got small molecules and they do different stuff. And so there's a couple of different centers, the one at Cornell and ours, which have invested in sort of graphic and materials that go into science museums. And in this particular case, we specialize in actual, they're called Nano Kids. That was actually the brainchild of one of our professors. And they kind of go through, my favorite one is teaching the concept of chirality through two identical twins who are molecules, actually larger molecules, but they can't quite fit together. So it's a really interesting little vignette. So it's a drama-based approach to teaching some of these ideas aimed at elementary school. And one of my favorite programs, which unfortunately we can't have anymore, is we had a really good welcoming science journalist to the campus, had funding to keep them there for a while. Fortunately, science journalism is gone. You can't really find a lot of science journalists anymore. You find a few, but given what the numbers that we had 10 years ago and what we have now, it's really a big shift in that particular area. But we still try to bring in who we can. And that was actually a very important part of our early work, particularly in communicating to the public about risks. A little bit about our teacher training, because I know a lot of you think about this. I just wanted to mention it so we could talk in various breaks about what we've done, and perhaps I could learn what you've done. So from our start in 2004, this is Noni, who started this whole work right around the time the center started in 2002, to now, one of our center points has been teacher training so that they spend a semester at Rice, and then they spend another semester at their school, but not in full-time teaching. So we buy them out of one semester. And during that time, what they do is they study how do the lessons and things they've developed pan out in another teacher's classroom. And so they have that sabbatical break, which has been a really strong motivation. And what we've been able to do in both of the settings, so this was our original one, which was middle school, now we're more focused on high school, is get the school district to actually match us in that buyout. We also provide them professional credit. And so the course, Nanotechnology for Teachers, they take in the spring. They usually get a fall sabbatical. And many of them also opt for a summertime learning experience. So what we found is that certainly we focus on active learning. We've heard a lot about that, so I won't go over some of the actual principles. What's been very interesting, although we've recently broadened, is Texas has a 9th grade integrated physics and chemistry science curriculum, which was where they sent science teachers who were the very youngest, because it was the place where they had the biggest problem teaching. I mean, the numbers on this class were pretty horrible. Half the students would flunk it. If they flunked it, they couldn't progress to 10th grade. So it's a really tough curriculum. And it matched well to nanotechnology, because if you know nanotech, it's about making the materials and then studying the physical properties. So many of the core concepts in Texas we could link very nicely to nanotech examples, and that's a lot of what this class is about, is linking those ideas between the standards that are present in Texas and what kinds of examples, hands-on examples, they could bring into their classroom. We really believe, and I think our data really suggests, if you want really effective teacher training, you've got to re-engage them multiple times and provide a professional path for them. So many of our teachers come back to us in a master teacher role. We have a big online community of all of our alums, and we have opportunities for them that kind of range and scale up as much as we possibly can. Because what we've learned is the real challenge is when you get one of these really great teachers, we were finding in our early classes, is they never stayed in teaching. They would leave science teaching. And so we made a really big point in our design of the sort of second part of our teacher training to keep them in the profession. Things like professionalizing, We've had a really successful Facebook page they all log into. They visit each other's classrooms. So they've created that scientific community. The last point that I'll make is we've experimented a fair bit with online teaching. And this is really the brainchild of John Hutchinson, who is our current ed director. He's a professor at Rice. He actually was up at Colorado for his sabbatical. And we tried it with a Colorado group of teachers and a Houston group of teachers for a semester. And the data on it was mixed. Both classes interacted. But what we found is that the Colorado standards and the Texas standards just didn't mesh. And these science teachers were so locked into teaching to the standards of their state, it became much more difficult in that blended in that single classroom to really connect the nanotechnology to both state standards. And besides the fact online is hard, what we have found working really well, Houston is a huge area, teachers will drive an hour to get to this class, is that we do online lectures and videos to supplement the once a week 3-hour class that they come to on Thursdays. And that's been a very, very effective way for us to broaden our participation. So we're up to 50 teachers and we have it way oversubscribed at this point. So a key issue, of course, is the sabbatical. Not every teacher will get their sabbatical, but roughly half of ours do. Some of the things they do is they actually make nanomaterials. One of the teachers I had in my lab said they can do this in the classroom. They go into the labs about every other week, spend about an hour or an hour and a half in a laboratory environment, learning some idea that emphasizes a concept from the class. This is an example where they're building a model. I put this up because it's ICAM. This is YBCAO. And the teacher has built the model, and then what they're doing here is playing around with liquid nitrogen and making these superconductors sort of levitate. We also do a lot of modeling of active teaching using clicker questions and other techniques in lecture to make sure the students don't just sort of get the pedagogy, but actually see it in practice in their own classroom environment. Okay, and the final sort of point I want to make that came out of this, because we have a couple of hundred teachers now, we're all still circulating, is that a group of them, one principal in particular who took our class, really became interested in online science materials. And so this is an example of one of the products, StemScopes. I'm not going to go through it. I wanted to bring it up because from my view and talking to my teachers in my program is that there is a huge shift coming in a lot of science ed, particularly middle school and high school, away from textbooks and on to online activities, interactive sort of models of learning that really abandon a lot of the textbooks. And so StemScopes has been approved by the state of Texas and has now, reaches 3 million students across the state. And it's really 5th through 8th grade now, and it's based on a lot of these inquiry and active learning work, but it's integrated with the state curricular needs. One of the interesting things about this that I wanted to bring up that's become kind of we don't have a school of education, but the interactive quizzes that are available here provide a wealth of information. A student might watch a video of a ball rolling down a ramp and how the ramp might influence that motion, and then be asked questions about it. Or at any particular time, you'll see student responses. Those are being collected, and so there's a wealth of data about what did the student view and how did they do on assessment. And I think that's going to be a really interesting sort of area to really investigate student outcomes and learning using millions of students potentially. This is not the only nonprofit that's set up to do this. There's a competition in the ed tech market now. Some of these companies are being capitalized in millions and millions of dollars, and it's a very rapid transition, and one that many of the teachers in our program, at least in Texas, feel is the future, mainly because you can put a student onto StemScopes, the state approves it, and it costs you about $5 versus buying the textbook. So the financial incentives are ginormous, I think. and so I think it's useful to reflect on how can you use these kinds of formats, which are easier to update. They actually, I think, are better at doing some of the active learning work, even though it's in an online environment. Okay, so I want to turn now to my last point, which is really just risk. And this is now moving away from education at the K through 12, and we have so many programs I didn't want to laundry list. It's really this, how do you nurture sustainable nanotechnologies, or how do we create nanotechnologies that society actually wants? That required us to reconceptualize how we did outreach and to whom. And really a lot of this was born on the fact that there are many examples, and I love to use Tinkerbell here. DDT cured malaria, one of the most powerful chemicals ever discovered in terms of number of lives saved. I live in Houston, you gotta have refrigeration if you wanna live. But each of these advances, which were chemically based, or you could argue materially based, had some sort of dark side to them. You know, in some cases, society said, no, we're not going to do it anymore. In other cases, it just cost huge amounts of money to clean up. And so the question is, what about nanotechnology, which promises to cure cancer, clean water, make airplanes lighter? You know, there's almost no promise, I don't think, that hasn't been made by nanotechnologists. So the question is, we're making lots of little tiny materials with special properties. Could those special properties have unintended consequences when they're applied to your body or used in our environment? And so that's really the genesis of a lot of the research in CBEN, and it's kind of one of our theme areas. And unfortunately, if you ask me today, I would still have to show you this cartoon. I love this cartoon because I think it sort of captures risk-based science. These people are in a car and there's a tanker truck. The scientific community is divided. Some say this stuff is dangerous and some say it isn't. And if anybody's ever been involved in communicating about risk, particularly materials and chemicals, that's kind of where we're often at. Is that, well, we're divided. You'll hear different things from different people. So how do you teach that and integrate that into a public's view of an important part of science and engineering?
Is that division just based on people's opinion, or is there actual scientific discussion?
It's really hard science, you know, so if you don't know, and I'll even pick, let's say, copper in water, you know, which is an area that EPA has only recently begun to regulate, even the basic regulatory science there has been in its infancy because copper can complex with materials in the water, it can influence its bioavailability. So a lake here in Colorado with a certain amount of copper could be totally different than a stream in North Carolina. And so, you know, it's our very complex system. And so regulatory science in general is extremely difficult. And you put a nanomaterial on top of that, which can come in a bazillion different forms. It's very intricate and complicated science and very early stage. So when somebody feeds nanotubes to a rat, one group finds the rats die, horrible deaths, really bad deaths, and the other group says they're just fine, you know, and they're both respected, good, reputable research groups. Well, the reason is the nanotubes that group one fed had a lot of iron and cobalt content, very reactive metals that were impurities that at the time of the study we actually did not know how to detect. We were not aware were there. And so what you're finding is that, you know, as you're doing these studies, you're also developing the foundational knowledge that you need to kind of also do the technology. And so there's a really interesting time period. If you go back to ozone, it took 20 years of data on the ozone hole before it became actionable for the public, or cigarette smoking. You know, it took a very, very long time before it sort of hit the tipping point and everybody agreed that it was bad for you. So it's a very interesting conversation about how does the public get to that point.
A lot of that is due to our emergence of doubt. If I know
Yes.
question. So there's
It's in
reasons
my
why.
talk.
Yeah, I'm not, and I would love to talk to you about cigarettes and the ozone hole because they're really interesting case studies about why did it take so
Climate change,
long.
Nuclear winter.
Right, but it doesn't mean that every time you have a risk, you're in that situation. So sometimes doubt is real, and sometimes doubt is manufactured or perhaps emphasized. So what we did in our outreach back 5 or 6 years ago is we realized we had a lot of different audiences, not just K through 12 and teachers, but everybody from government regulators who were coming to us for information, to, you know, companies who became big funders of these kinds of activities. So we started an unusual outreach activity called the International Council on Nanotechnology, which exists today. And our premise was you needed to get all the different people in the room, those who felt nanotechnology was probably bad, those who wanted to make a profit off of it, and maybe the academics who were neutral, although sometimes, not always, and get them to basically commit to one thing. There was going to be a debate about when and how to use nanotechnology, but you wanted that debate to occur at the highest possible technical level. That's all we could really do. And that, as you'll see some examples of what that concretely meant, but that's really all we can do in these early stages, is what is the actual data like, and can we provide it to the public with as neutral of a platform as possible. So we have done a lot of stuff. We have an incredibly popular thing. You know, a lot of you who might be at universities take our databases for granted. You can go to Web of Science or PubMed and get any paper in the world. Well, if you're somebody in the general public, you're trying to decide whether or not to use a sunscreen with nanoparticles, you don't have those access to those. So we've been populating a nano EHS literature database that includes a lot of categorization and information, and in fact kind of an Amazon-like review so experts can review the papers that people find. You'll see they have a certain number of stars. And anybody, it's a free database, anybody can search it. We only hold the abstracts, we can't provide the papers for obvious copyright reasons. And this is hand populated. So we have a couple of grad students who every quarter go through all the literature. They do some categorizations that you don't find on the database, conventional databases, and they post them. So this is a broadly used database right now. A public information portal, everything going on in the area, of course. We do things like a nanomaterial handling survey and have since published standards on best practices for workers using nanomaterials, those kinds of activities. I'm going to give you one example because it's a really good one. So this is a friend of mine, Andrew Maynard, holding a vial of carbon nanotubes. And in fact, this is a group of people, there's Andrew's name, but it was done by Ken Donaldson, this work, which basically showed asbestos-like pathogenicity. You know, mice who were exposed to these materials developed pre-cancerous symptoms that look a lot like exposing them to asbestos. And so this paper, as you might imagine, could be first page headlines, especially when you realize carbon nanotubes are actually used in commercial products. In particular, in Japan, they're used in blankets that are often anti-thermal or used to sort of put fires out. Really, carbon nanotubes. And so we imagined all these headlines, but this group is very integrated with this organization, ICON, which has a very complex governance structure. In fact, they were academic members of it. And they asked us to do what we call a backgrounder. So they gave us an early view of the paper. We wrote a backgrounder. We went out to all of our science journalists. We had a pretty good network, made sure they knew about our site. So our site was actually on Google, one of the top sites when this paper came out. And we have a really intricate discussion of exactly what they did in the experiment. They did actually an intra-abdominal injection. You didn't inhale the materials, so there were a lot of questions. But probably the most valuable to folks when they did the survey later, because thousands of people hit this site, were the author. We have a multi-wall nanotube manufacturer. We have somebody from environmental defense. We had video interviews done with all of these folks where they answered similar questions about this work. And what it served to do is it actually damped down a lot of the extremism that you could have had over a paper like this. It kind of put it into context, what's true, what's not true. And I think that that kind of information in these early stages where you're really just trying to figure out the science can be valuable, because an overreaction to a paper like this is just as damaging to finding the truth as an underreaction. So the last point I want to make about risk, because that was kind of an audience, you might argue, is that really the public? Well, thousands of people hit it. They were a subset of the public. They might be regulators from all over the world. They might be manufacturers. They're an important component of people to communicate with. But what I've discovered in doing this now for a decade is that when you have a risky issue in science, something about risk or fear, you know, it's hope and fear are the two motivators, right? You have a really interesting way of engaging the public, particularly adults. So I've done, I think I was counting, 6 different dialogues. And I started to do these activities in Europe in particular, but I also did some in Australia. I did one in Singapore. And the concept is when you have a controversial scientific issue, this really comes, I believe the Netherlands is ground zero for this set of research. You don't want to engage in the public in a one-way dialogue. Oh, it's all safe. Trust us. Well, why should we trust you if you can profit off of his success, for example? Or you're an academic whose whole research career has been tied up in this. So what they really do is something called a dialogue activity. And I'll bring up an example that I had at the University of Oregon, which really was an excellent example of one. So what they do is they target adult learners. And they don't say, come and see our exhibit, which is going to just basically be this sort of passive thing up on the wall. But we're going to ask you a question. And your whole group, however big it is going to spend the 2.5 hours answering this question, coming up with a resolution. There's like Robert's Rules of Orders for everybody to participate in. And then we're going to pass that opinion, public opinion, informed public opinion is I think what they called it, onto a larger group who's going to disseminate it and have it as part of the public record. So we'll promise to submit it to regulators, we'll work with it. So there's sort of an end goal here. But this is one of the questions. They had several questions. So I had known when I had done these in Switzerland and in Australia, hundreds of people would show up. I was stunned on a Tuesday night, there would be, and they were all walks of life, clearly science interested. But they would be often in round tables. There would be no formal lecture. They'd be given a piece of paper, and you would be floating around after people, and you would go to, it's like being at a wedding. You would stop at a table, and they would start to ask you questions. And then when they got tired, you would go off to another table. And so particular interest for me, because we actually have published a lot on sunscreens, and I don't know if you ever read Consumer Reports. I'm so proud that I have data in Consumer Reports. We have the TM images that appeared in some of the articles about sunscreens a few years ago. But in this kind of interaction, what I found was a high level of engagement, and the follow-up data showed these people kept coming back to their sources and really relished that opportunity to have an ability to have a decision, make a decision. So even in this country, you're seeing it more and more with some of the Nanotech Science Museum activities. So some of the things that I learned about it was very hard for me. Clearly, I'm used to talking. It has to be a two-way conversation, and you have to really be interested in what they have to say. I was stunned in every case at how wise their decisions were. They really came away with kind of the right answer, and they managed their own internal conflicts in interesting ways. It's active learning from adults in a museum format. It might not work, with certain age groups, but it's a great way to engage adults. We've actually done more of this in our alumni colleges at Rice, and it's been very successful in that setting as well. There's a context for learning a lot about nanotechnology. So it's not, here, let me spit out information, but it's make a decision. What's your opinion? And I've been stunned at how I've heard from a lot of people these are very popular programs. One that I would strongly, that I'm really interested in seeing more of, because I would attend one, is geoengineering. So there's a lot of topics that have been done. I don't know that geoengineering's been done yet, but there's a move afoot to dump huge amounts of particles into the atmosphere to cool the world. And that's a hugely controversial issue on a number of fronts. And it's the perfect kind of place to engage adults and have them sort of consider what we should do about it. The challenge is, of course, so they write something, who takes that opinion and who is then the sort of keeper of that knowledge? And I think that that's been one of the things at least the nanotech community struggle with. So our center has some examples that we've kept and we've transmitted for public comment. For example, the FDA opened up a public comment about sunscreens and if they should consider labeling them. Nano materials are in them. And by the way, you don't know when you buy sunscreen. And so we asked Oregon, and then we submitted the opinion from the public as a comment. So that's one of the things you want to promise is some way for their time to hit the world. Okay, so those are my comments, a little bit about teacher training, a little bit about using risk as a way of engaging the public and realizing there can be multiple points of view and sharing that with them. So some of the areas I think are in the future is this whole online education business, both in teacher training and how I think they're going to be doing science education, but also certainly what's happening in colleges. Rice is just committed. We're one of the groups now on Coursera, and we're doing a nanotechnology, the basics class, a small class. It's only about 8 lectures, but we want to use what we call a Nova Light format, and that's going to expand potentially public engagement in some ways. I think you can exploit controversy to get interest, and I think adults are a really interesting population for this, and I sort of have some examples that we've been kicking around, although they're not my area, to work with our local science museum to do some of these. And you would bring in experts from the outside to sort of debate it. And finally, I'll just say, one of the things about communication, and this is now not just outreach, but broadly public communication in this area, is that it has never been more important than now to engage the public. I just came from DC. I do wear an administrative hat now at Rice. And the climate for public funding of science and education is just as bad as it has ever been, and it will get worse. Just because of discretionary versus non-discretionary kinds of issues. And as a Senate staffer said to me when I was touring the Hill, science research has no constituency. As much as we teach and educate, we haven't been able to really engage people. They engage in diseases, which is good, but we haven't been able to make that kind of engagement broadly, and that will cost us, I think, certainly in our country at the federal level. And I would at least put forward, and this is a controversial thing, that we may be part of the problem. Those of us who are the educators and communicators own part of this. And I think that I'm going to give two examples where I often have lively debate, and I'll throw them out. So when you think, and I'm talking about broadly about public engagement, not so much K through 12, although the question is pertinent for all, perhaps. So what is the goal of the engagement? You know, do you just want them to engage? Do you want to educate them? Do you want to teach them something? Or do you want to entertain them? And what I found is I was recently giving a lecture about science communications at the National Academy, and I used the example of Mythbusters. Who has seen Mythbusters? And my kids are like totally addicted to Mythbusters. And I got some serious static because scientists feel that it's not an accurate reflection of science. They push back on things like CSI and Mythbusters. It's communications. They're not really teaching pure science. So our own scientific community looks at those examples, which I don't know if you've seen the stats on how many young people are watching Mythbusters. I honestly wish they would do a lot less with guns, but putting that aside, there's content in what they do, and they are engaging people. And so one of the questions is, why does our community have a negative reaction to those kinds of examples, or do we? And where does that come from? And I think the other piece that we've touched on, who reads The Onion? I love The Onion. This is my favorite title, NSF study, science hard. This is a paper, they have hard. It's this concept that we make science hard because we know it's hard. It's hard to learn to do what we do. And how much of our own culture makes it difficult. I would say particularly the lecture about college teaching, I think, highlighted that. And so it's an interesting flip of what if you were to give a class and never ever grade anybody, but give them as long as they needed to get an A in your class, to achieve your learning objectives at the highest level. So if they flunk your first test, they get another chance. This concept that we sort of hold the standard and you must achieve it in a certain period, what if we could get rid of that? And how much of this do we do ourselves? And I think this is also an important dialogue. So I think those questions are important. I don't have the answers. I just put them out because I find they generate conversation. So with that, I have to thank these folks, particularly John Hutchinson and Kristen Klinowski, who are really instrumental in some of the programs that I talked about, particularly the teacher training for John and ICON for Kristen. She's now in DC doing her best to educate staffers on the Hill. So with that, I'll be happy to take any questions. Yeah.
Yeah, I was interested or kind of shocked at what you said about cutting back or scaling back, or I guess even eliminating your outreach to science journalists because there aren't any science journalists anymore. And it's certainly true that there aren't many newspapers. You know, every little newspaper or medium-sized newspaper used to have a science reporter or science/health/technology, also covering the local laboratory. But at the same time, I don't think they're disappearing, but they're moving into different media.
Right.
It's this very strange transition period.
Yeah.
You know, I had mentioned that we do this Santa Fe Science Writing Workshop, and we just had our 17th annual workshop. We had 50 people who came to the workshop to learn more skills about science writing because they want to communicate. They're finding like niches on the web, or
they're bloggers,
or being freelancers.
I think they're pretty much freelance now, which the way we did our program, we asked for a match from the employer, so we matched whatever the employer would pay.
Yeah.
And so that we had a little bit of money to do it, and it wasn't an easy sell with the NSF, I can tell you. So what happened is we lost any ability. So the guys I knew at the Washington Post are all moved on, and you know, Woodsy, who we knew in Dallas, moved on. So we still have connections and databases. Half have gone freelance, half have gone into doing something totally different, like communications for a university or somewhere else. So I think the number's just smaller, and it may just be that we were relying a lot on our communications people at Rice to sort of put us in contact with those networks, and I think the networks have shifted a lot. But my sense is that it's harder and harder to find somebody who covers it as a beat. It is more the freelance kind of world. And so, but I think outreach to the journalist is critical, and I'm glad to hear that there are people out there who are making a living doing it, and I will correct that assessment. Yeah.
Oh, I just wanted to tell a little story. I loved your point about giving people endless amounts of time, which is what I hear often from my Asian students, why they're better. And math and hard sciences is that the classes tend to wait until